Okay, welcome and thank you for attending this session. It's late of the conference, but I hope you will enjoy it. Today we will talk about it's a performance topic, and we will reveal some benchmarking and a comparison across three basically JVMs that we did together with Florin. And let's see what is the agenda for today. So we'll kick it off with a bit of introduction. Then basically we will share with you some of the benchmarks. Just to give you a number, we have a lot of them. For example, we have 270-ish benchmarks. Of course, we won't present so many because it will take probably the entire day long. Nevertheless, we extracted a few which we consider a bit more representative for this talk, and based on those, we will try to end up with some conclusions, some challenges that we had during this analysis, what we learned, and of course the future work, because we will probably don't stop here. Okay, so few words about myself. I work for Raiffeisen Bank International. I also do trainings, and this is also a bit of commercial slide. So if you want some of these trainings, or these trainings might look interesting to you, yeah, you can get in touch with me and my colleague.
I'm Florin Blanaru. Currently, I'm a senior software engineer at OctaML. Previously, I was a research software engineer at the University of Manchester, where I heavily contributed to Tornado VM, which is a plugin to OpenJDK that allows you to run Java code on GPUs and different kinds of accelerators except CPUs. In general, I'm interested into language runtimes, compilers, and performance analysis and tuning, and that's why I'm here today.
Thank you. Good. So basically, our talk, it's based, everything what we share today, it's public. It's public partially on GitHub. So basically, the full repo with the benchmarks, it's on GitHub. But we also wrote an article, and the backbone of our presentation is this article. So, and I will also tweet the slides after this talk. This is the article I was talking about. It's focused on JDK 17, right? So you know that yesterday or 2 days ago, it was released Java 20. Unfortunately, we will present 17. Out of curiosity, who's using JDK 17? Okay, very good. Who is using 11? Okay, and the majority? 8? Okay. Okay, I hope you'll migrate at some point to at least the ones that are using 8 to at least 11, but in my opinion, I think it's interesting to start with 17 as well. Okay, so this is basically the article, what we collected and included in this talk. It's based on the presentation. In summary, what we will talk about? We will talk about 3 different JVMs. The first one on the left side, it's called OpenJDK. It's basically, it's OpenJDK hotspot. I suppose the majority of you are using this JVM on production, right? But then it's interesting also to compare, for example, from a compiler's perspective, also the Graal VM Enterprise Edition and Community Edition. It's written down here. And the presentation is from a compiler perspective. So we don't talk about garbage collectors. And also a reminder, we don't talk about native image. So we just talk about compilation and runtime, right? So nothing, it's about AOT and native image. So this is basically the purpose of us is to zoom inside each of these and to tell you, for example, what we found out in this research, in this benchmark analysis, what are the strengths and what are the weaknesses of all of this. The configuration I just briefly described on this slide. Basically, we used 2 different architectures. We used Intel x86-64, but we also used the ARM. So both of them and a bunch of other configurations, especially for the Intel, we tuned a bit the OS to mitigate the noise. For ARM, we just let it implicitly, for example, for Apple MacBook Pro, we just let it as is. We use GMH, so basically the entire benchmarking, it's based on the GMH. Are you familiar with GMH? Are you using GMH? Okay, just a few. Have you heard about GMH? Okay, just a few. So basically GMH, it's a tool, you can use it for example, to write micro benchmarking. It's not suitable for macro benchmarks, but it's very good and handy tool to use short snippets of code and to analyze those snippets of code, how they behave. Okay, so now let's zoom inside the benchmarks. As mentioned, we just included here a few of them, but there are a lot. Before doing any benchmark, you need to analyze the infrastructure. So before even going into comparisons between these three hotspot JVMs, right, OpenJDK, Graal-E, and Graal-CE, we had to understand if the baseline is the same. And what it means for us, the baseline, basically, I'll jump to the code. So the baseline, I hope if I zoom in a bit, it's sufficient enough. The baseline for us, it's just assessing, for example, how much time it takes to return a void method. How much time it takes to inline, just an empty method. How much time it takes to don't inline a method. How much time it takes, for example, to use black holes. Black holes, it's something specific from GMH, and this is very important because if you try to compare one JVM against another, if this baseline is not the same, there is no sense to go further and do further comparisons. For example, if you are using the OpenG9, this is not fully compliant to this, so that doesn't make sense to go further and trigger other benchmarks. So this is the thing. We tried basically to understand if the baseline, at least it's the same. So in our case, I will show the graphs. One more before describing the graph. Everything was rendered by us based on the results. We wrote a bit of code in R. In our language programming language, and basically what this means, these are some bars, and each of these bars during the entire talk corresponds to the response time. So implicitly, if the bar is shorter, the response time is lower, so implicitly it's better. And this is one more point. So shorter bars means better. And the second point is here, down below, there is the legend. The blue one corresponds to OpenJDK, implicitly C2 compiler. The one in the middle corresponds to E, Graal from the Enterprise edition. And the one below, which is this yellow one, corresponds to the Graal implementation, the compiler, the Graal JIT from the Community Edition. So we have three: OpenJDK, Graal-E, and Graal-CE. And in a nutshell, we have two compilers: Graal, just-in-time compiler with two flavors, and C2 from OpenJDK. And as you can see here, everything is more or less the same except this object syncing. This is something that we don't use a lot in our benchmarks, but nevertheless, for example, to return objects, to use this black hole, which has, it's basically a no-op implemented in the compiler. And in 17, also Graal has this implemented, not only OpenJDK. So as you can see here, everything is the same. It matches. So now, because everything, the baseline is the same across all of these three JVMs, it gives me a sort of confidence to go further and to trigger the other benchmarks. And now, this is the first one. So this was basically to set up a bit the stage. Now we will share with you some of our benchmarks and what we did so far. The first benchmark, I just included it here because I'm doing, for example, also a lot of RESTful microservices development. And basically, when you do like this, you declare your interface, the RESTful interface, why not in OpenAPI? Or if you use Swagger, doesn't matter. The thing is, at some point you use enums, right, in that declaration. And the problem with this approach is if I switch back here to this example, so this is a real use case. So this is my OpenAPI, it's a YAML file, and here it's basically this currency. One second, so yeah, this is an enum. And when, for example, I'm using this approach, which is called API-driven development. First, I generate the YAML interface, and then I basically generate all the interfaces and the models. And this is something which is auto-generated by the Open API plugin. And it gives you, for example, if you search for a string, it returns you the wrapper for that, the enum corresponding to that value. This is useful because, for example, when you receive a request in your microservice, if you use JSON, for example, you receive it in string, but of course you need to deserialize it and create the wrapper object during the runtime. And of course, because everything is string, it needs to matches in this loop. So this is basically the context behind this benchmark, but this is not the benchmark in essence. The benchmark, I will jump to it, and this is actually our benchmark. So here I just declare an enum with a lot of values, explicitly a bit longer, and then I use two values of it, the cached values. So basically, every time when I iterate through this, I'm using the cached values, and the second part is I'm not using the cached values. I'm always, because this is the trick, when you have an enum and say dot values, basically the array itself, it's cloned. And it creates a lot of allocations, basically. And this is not really a recommendation. That's why I also wanted to compare again with the cached values of those enums. So basically, I cache the array, and I'm reusing it in the different benchmark method. Okay, and what we got basically, so you expect that all of this will behave more or less the same, right? Because it's just an enum or a cached version of the enum, and there is a matching, it's a equals between the strings. I'm still waiting. This is, by the way, a talk where I really need a good connection because everything it's public, so I'm switching back and forth between the PDF and the article. As I see, it still takes a bit. Yeah, okay, good. So basically, what are the results for the enum values and the cached enum values? These are what we got. I would like to focus a bit on the cached enum values because as it is looking here, C2 does a better job than Graal. It doesn't matter. Oh, it does a better job than Graal, JIT from E and also CE. And why this is happening? Because the code is very, very simple, right? So you saw it here. So in this version where they are cached, the code is like this, basically. What's the problem? Why C2 is better than the others? Well, we took a bit of analysis. Let me zoom a bit into this. The explanation for this in case of C2, basically, is that for string comparisons, C2 uses an intrinsic which is faster than the intrinsic used by Graal, E, and C, but they both use the same intrinsic. So this is the intrinsic call, for example, by Graal. What says that intrinsic? Because you know strings are represented with byte arrays, right? When you write a string, it's a byte array. And basically what Graal, the compiler, does here, it tries to compare, when you say equals, it tries to compare those two byte arrays by using that intrinsic. And this intrinsic is slower than the intrinsic used by C2. And yeah, this is probably it will be improved, I don't know, but this is the explanation why, for example, for string comparison, at least C2 does a better job, at least for these tests. And yeah, I didn't mention a bit, if you might not recognize that type of syntax, this is instruction code, this is what we call the assembly code. The problem, or fortunately or unfortunately, to understand these things, you have to a bit zoom inside what happens and to be able to provide some explanation. So this is one use case where we found it useful, and also to provide to you a reason behind. So this is one use case. Lesson learned from you, try to use, for example, these cached Enum values, because what intrinsics are, you cannot influence, right? You don't know, basically. But at the first glance, at least in these benchmark, yeah, C2, it was a bit faster. Next one is about log coarsening. What is log coarsening? Let me jump first to the source code, basically. This is the source code. It has a lot of benchmark methods. I will just focus on the one which really matters, and is this one. Log coarsening means basically, based on some analysis, the compiler can basically merge the synchronized sections if they are one next each other. Because here it's anyway stupid, right? You are in the method, right? So you say synchronized on this, synchronized on this, synchronized on this. You would never write such code, have you? No. But when this pattern might occur? This pattern might occur, for example, even if you don't write it like this. If you, for example, have method A, and method B, method C, and so on, if one method calls the other, and inside each of these methods there is this synchronized this, after inlining, you can end up with something like this, right? So during the runtime only, because up front, nobody will write it unless he wants to make some jokes with his colleagues. So this is one point, and this is the interesting part of this benchmark. Of course, there are other benchmarks, other benchmark methods in here, but yeah, I will focus on this one because this is what matters to what's worthy to be presented. And there is one in addition point which I'd like to tell you about. Have you heard about bias locking? Bias locking was basically an optimization in OpenJDK, which was supposed to help programmers that abuse of synchronization. The thing is, until JDK 15, this bias locking was enabled in OpenJDK and helped, for example, the legacy code and the legacy APIs that used a lot of synchronized. Even if you don't have contention, basically, even if you don't have multiple threads calling the same synchronized method, it still helps you because basically if there is no contention, there is no op in the instructions in the assembly code emitted. So basically it's for free. It's like you don't do synchronization at all, but only if there is one thread. Of course, if there are multiple threads, it falls back to some other things. But if there is no contention, this is very fast. And this is why, for example, here with bias locking, this is implicitly enabled until 15, but starting with 15, this is without bias locking. It makes sense to be without bias locking in the newest ones, because bias locking on modern hardware should not count too much, basically. And this is the one reason. The second reason is if you might have heard about Shenandoah GC. Have you heard about have you heard about ZGC? This disables, for example, biased locking, because these are almost fully concurrent collectors. And basically, if you have this bias locking mechanism enabled, you need to do a save point, a pause, basically. And this collector do not afford pauses, so that's why they disable implicitly. Even if it is enabled, if you use, for example, on 11, let's say, with Shenandoah, it gets disabled. Okay, so this is just a bit Yeah, this is just a bit of preparing my test. Now let's focus on this nested synchronized. I'm getting back to my benchmark. So this benchmark, where was it? Yeah, yes. So this is my benchmark. Let's see, right? So this is the way how I wrote it. And here, what you can see, basically, you can see that this C2, it's really 3 orders of magnitude slower. This is huge. This is huge. This is this is nanoseconds, it's microseconds, so in comparison to nanoseconds. And of course, this is influenced by the number of nested synchronized sections, because if I had, for example, 64, it will be even bigger. In comparison to E and the just-in-time compiler from E and CE, they were able to basically optimize it and run it very fast. The same here, it doesn't matter if it is bias locking enabled or disabled. You still see a very long bar. What's the explanation behind? The explanation behind is that there is basically the C2, the OpenJDK compiler, tries to, one second here, he tries to optimize that nested synchronized, and it spends too much time and it gives up and falls back to the interpreter. And this is why basically it's explaining in difference. It's so big difference because one is run into the interpreter, with the template interpreter from OpenJDK. The other ones are compiled. And for example, I think I have it here, yeah? I like very much the way, for example, how EE did this, as you see here, because there is no contention, there is no compare in exchange swap instruction emitted at all. So everything is just inlined, and everything is sequentially, and all of these adds corresponds, for example, to this, correspond to this result plus, right? So what you see here, everything is in line, it's in sequence, and there is no synchronization block in between. So it's very nice. So at least the EE just-in-time compiler did a good job in basically removing the unuseless synchronization. And if there is bias locking enabled, or disabled, sorry, without bias locking, so here you see, even if you use bias locking, if there is no contention, it's for free, basically. You don't have any atomic compare and swap operation. But if it is, it's just the cost of this lock. So this is basically the difference when there is no contention. And then everything else is coursed, and yeah, that's why basically it's pretty much difference. All the other benchmarks from here were more or less the same, but what was basically a matter of interest was why one it's so slow. Maybe this could be improved, right? Because it doesn't look very good. It could happen, yeah, I don't know, but yeah, it's something that we found out. Next benchmark is that local allocation store. What this means? Basically, it relies on the fact that I'm allocated something in one instruction, and the subsequent instructions basically invalidates what I previously allocated. Let me show you the code, because it's, oops, no, sorry. It's basically simpler like this, and I will be focusing on 2 methods, basically. I will explain you, because I know what are the difference. So let's find this object. Yeah. So I will present you this wrapper object baseline, which basically returns a new wrapper. And this new wrapper, it calls the default constructor, which is down below here. And the default constructor is, sorry, this one. So basically, in the default constructor, you allocate all of these objects from 1 to 8 and just return it. That's simple. And the other one, what I mean by this dead, to remove this dead store allocations, Basically, the other constructor is, one second, is this one. This is a bit more difficult, but I'll try to explain. So basically here, what it does, this method, here you allocate 8 objects in row, in sequence, from 1 to 8. And then you pass all of this to the explicit constructor, and the explicit constructor is down below here, and is this one. And what does this constructor? Basically, it calls the default constructor, which triggers again allocations, right? And then basically it resets all the references to the initial ones received as parameters. So basically, to conclude, everything which is here, it's useless. Correct, because you call this one, it's calling this, it allocates, but then you basically reset the references to what you have received as input parameters. And this is the thing, if the compiler, for example, it's able to inline this default constructor, it should remove the allocations, right? Because those allocations, previous allocations were nonsense. Let's see if both of them are doing the same, or all of these 3 are doing the same. In case of, for example, wrapper object baseline, Graal E compiler, the just-in-time compiler from E, was faster. And C2 and E version were more or less the same. And if I have to refresh, what is this object wrapper baseline? Is basically I'm saying new wrapper, and I'm allocating 8 objects and I'm returning it, right? And why E was faster? And again, it was faster. Sorry, not. I'm jumping back here. It relies. So this is, yes, I know it's a lot of. It's a lot of nice code for the end of the conference. But the problem is, I'll try to just summarize it for you. The thing is, Graal E, right, just-in-time compiler, does a very nice job in basically he tries to assemble the load and store operations in order to benefit of the CPU pipelining and prefetching. So basically, when Graal E emitted such instructions, those were grouped in a way that it benefits of the CPU basically helps with this prefetching and pipelining. And this is why basically these loads and stores were grouped. And this is the explanation basically why, for example, in such a case, the wrapper was faster in case of E. CE and CE, yeah, the yellow one, and the C2 basically don't do this kind of, yeah, nice optimization. They don't group these instructions. The second difference is for this wrapper object. So this is basically our intention to test if those redundant allocations were removed. So you can say new something, and in a subsequent instruction to say AAA equal new object, and in subsequent instruction you say AAA equal another new object. Again, E was faster. I can say C2 and C just-in-time compiler were mainly the same. But why E was faster? The enterprise one was faster. Again, let's get back, and I try to explain a bit. This is a bit, yeah. Have you heard about thread local allocation buffers? Basically, each thread, when you try to allocate something, it allocates in this TLab. It's a buffer, it's a memory area where each thread allocates. The thing is, because you have multiple threads inside the JVM, they both can concurrently allocate on the heap. Because otherwise, if everybody will allocate in the heap, there needs to be a sequential operation. You can disable TLabs, but everything will go much slower. And this is basically this buffer, which we call TLab, has, of course, it's limited. And if it is, if the new allocations doesn't fulfill this TLab, of course, the new TLab, it's requested, but you also can allocate with a slow path. But here, what does and why it's so fast, for example, the E, the E JIT, It's because it does a nicer optimization. What it does here, you see, first of all, it eliminates all of these redundant allocations. And the second point is, you see these 8 basically allocations. What does EU? EE checks only once in the beginning if all of these 8 objects fits inside the T-lab. It's one check. And this, if everything fits inside the T-lab, it follows the fast path allocation, basically. And with this fast path allocation, everything is allocated in row. This is an example with 3, but the same happens for all. And if this is not happening, the case for C2, right, and the case for CE JIT, it's complicated to, yeah, there are a lot of terms. So for these 2, they don't do this nice trick. They don't check once for all, and they check for each of these new allocations. So every time you allocate, it checks. Does it fit inside the T-lab in the buffer, in my local buffer? Yes, allocate. For the second one, is this, does this fit? Yes, and so on and so forth. And this is basically the overall idea why this is actually faster, so fast in Graal E for just-in-time compiler. Yes, I think I've said, yeah, that's a lot of stuff. Let me close all these tabs, because the next benchmark will be presented by Florin, right? So I think I'm done with this. And yeah, you need a fresh environment.
I hope you can hear me properly. The next benchmark is the Mandelbrot Vector API benchmark. It tests the performance of project Panama's Vector API for computing the Mandelbrot set. In case you want to know what the Mandelbrot set is, it's just a nice benchmark. It creates some nice fractals that you can visualize, and it can be easily parallelized and vectorized as well. Just to give you a heads up, the Vector API is still an incubator module in the JDK, and it's subject to change between releases. So let's check out the source code. The baseline of this benchmark is the one where we don't use the Vector API at all. So we just use normal instructions to compute the Mandelbrot set. Then we have the vectorized benchmark where you use the Vector API, a double vector species. In my case, the length of the vector on my machine is 256 bits, I think. Right. So let's check out the results. Well, overall, one second, let me zoom on this. Right. So overall, we run the benchmark with multiple iterations and sizes. The trends are pretty much the same between the baseline and the vectorized. So we're just gonna jump straight to the 2000 number of iterations and the size 512. We can see that in the baseline, all 3 JITs perform the same, while in the case of the vectorized benchmark, where we use the Vector API, C2 is quite fast, it's much faster than baseline. Then comes Graal EE, and then finally Graal CE, which is much slower. So why this happens? Well, if you run this with perf and check the hottest regions in the code, you can see that CE stays pretty much in the benchmark method all the time. Sorry, C2, and then CE calls into some methods. This is because C2 has the intrinsics fully implemented in the compiler. Graal VMC has no intrinsics, or very little intrinsics. And then Graal VMEE has some intrinsics, but not all of them. And this is why we see the difference in performance. As I've said, this is an incubator module in JK 20, I think. It's yet incubator, and it's subject to change. So it's good to know that in the future, probably Graal VME and C will be much closer in performance with C2. So next benchmark now is the Megamorphic method call benchmark. In this benchmark, we try to measure the cost of virtual calls with a different number of targets. And then we have a second benchmark as part of this class, which checks the performance manually splitting the call site into monomorphic call sites. I'll try to explain what monomorphic and bimorphic call sites are in case people want to know. But first, let's have a look over the benchmarks, right? And I'll try to explain it as part of the code. So this benchmark has an abstract class, which is called CMAF. And this abstract class has multiple implementations, which is alg1 to 8. The abstract class CMAF has some fields, C1 to C8, and then each implementation will increment a different field. Doesn't really matter, but yeah, it's a very small method, right? The virtual call benchmark will iterate through the instances and will just do instance.compute on an array of CMAF instances, right? Then we have the devirtualized monomorphic benchmark, which, if you look at this code, it looks very ugly, right? I mean, who would write this? You would never write this kind of code in production, never, ever. But I'll try to explain why it looks like this, right? So we also have an array, a class index array, and then inside the loop, which is similar to this one, we switch on the array on the class index. And then we have multiple call sites where we do the same call, instance.compute, right? So what this happens is that the JVM will profile each call site, and if you have a dominant target at the call site, then it's going to replace that virtual call with a static call, which is much faster. It doesn't jump to the virtual call stub. So let's look at the results, where I also have some pseudocode, high-level pseudocode to explain what a monomorphic call site, a bimorphic call site is, and what kind of optimization C2 and Graal do. First, let's look at the results, and then I'll try to explain it while explaining the results, right? So I'll explain the explanation of the results into two. First, we'll look at the virtual call, and then we'll look at the devirtualize, right? So when it's monomorphic, it means that there is a single class that implements all the instances in that array. When it's bimorphic, it means that there are two classes, and it has to do a virtual call between the two classes, right? When you have Megamorphic 3, it means that you have 3 implementations of the abstract class. When you have 8 or 7, it means that you have 7 implementations. Let's look at the virtual call first. For virtual call, we can see that all the 3 JVMs perform quite similarly. For bimorphic, it's the same. For virtual call Megamorphic 3, we can see that C2 spikes. So why this happens? Well, it's because C2 is no longer able to do a static call here. It will do a virtual call every time. On the other hand, both Graal EE and CE are able to do some tricks, which I'll show you later, to basically save some performance. And you can see that the trend for virtual calls is, as I increase the number of targets, Graal VM EE becomes slower and slower, while Graal VM CE stays the same, which is interesting. So now let's go and explain what a monomorphic call site is and what a bimorphic call site is. So a monomorphic call site is like when you have a single type, C2 does this optimization, and Graal EE and CE. You basically add a guard in the assembly code that you generate, which says, if my class is instance of type 1, I will do a static call to this method. Otherwise, I will de-optimize. This is what C2 does. When you de-optimize and you regit again, when you generate the assembly code, in C2 is going to be a virtual call. For a bimorphic call site, you basically have pretty much the same thing, but you check, do I have an instance of type 1, then I'm going to do a static call for type 1. Do I have an instance of type 2, static call for type 2, otherwise I'll de-optimize. This is what C2 does again. And Graal CE and EE do the same thing. Going back to this, so C2 will always do a virtual call. Graal VM CE will basically do the instance of check for up to 8 targets. So you duplicate this for 4 times, I guess. and then GraalVM EE will do this thing where instead of de-optimizing and then rejitting with a virtual call, I will check for the first three targets, which are the most common, and then otherwise I'm just going to take the slow path, and then I am going to do a virtual call for the remaining targets. So in the case of our benchmark, we can see that we tend to increase the benchmark time with the number of targets with GraalVM EE. This is because there are more and more targets in our array of instances which go through the virtual call path, right? And then to explain the devirtualized to monomorphic case, because in the benchmark, as I've said earlier, we had multiple call sites. The JVM generates a profile for each call site, right? So the JVM is able to do a static call for each call site, regardless of the number of targets that you have. This is the trick that you get. You might do this if you are, I don't know, into fintech or something like that, but not otherwise. And we can see that the JVMs pretty much stay low as the benchmarks are pretty much similar. They're fast. I hope that kind of makes sense. Let's look at the next benchmark, which is MPE throw benchmark. This one tests the implicit versus explicit throws of exceptions, of null pointer exceptions, and catching them in a hot loop. If you check the code, it does this for static and it does this for implicit and explicit throws. In the explicit case, I check for null and then I throw an exception. In the implicit case, I just do a field access and I might throw an exception if this wrapper O is null. So let's check the results. And this happens in an array. We catch the exception in the benchmark and we don't do anything with it, right?
It's very similar to our production code, right?
Kind of, yeah. Right. So what happens? We have a threshold. Threshold is like the number of nulls that we have in the array of instances. Threshold 1 means all of them are null. Threshold 0.5 means some of them are null, right? Okay. The trends are the same between threshold 0.5 and 1, so I'm just going to look at threshold 1 for the sake of it. Explicit throw NPE, where we explicitly check for null and throw the null pointer exception, they're the same, the 3 JVMs. For implicit throw NPE, we can see that Graal is both E and C are kind of slow, and then C2 is very fast. So what happens? It's easy to understand what's going on here by looking at the flame graphs, if you are familiar with this kind of stuff. There's this thing called async profiler. You can run it as part of JMH. It's an open source project. And it shows you, it profiles your code and shows you where do you spend most of your time when you run your code, right? So if you look at this part, you can see that most of the time for C2, it's being spent in the benchmark and then in the exception handler in the runtime, in the JVM. If you check the same thing for Graal, you can see that Graal spends some time in JVM CI, which is, it's another thing, we don't have to explain it. Basically, it creates a new exception, and then when it creates that exception, it's going to go and create a new null pointer exception, and it's going to walk the stack and fill the stack trace, which you might need later when you catch the exception, right? So why this difference? Well, because C2 has an optimization, which in case you don't need the stack trace, you can directly jump to the handler, the exception handler, and you don't have to create the exception, right? It's called fast throw, and it can be disabled with this option here. We actually disabled it, and the flame graphs after this look very, very similar between the two JVMs. Next one is the recursive method call. This one tests the performance of recursive method calls in classes, interfaces, and then Lambda functions as well. So if you are able to inline, you can basically jump a couple of iterations in the benchmark, so you will be much faster, right? So let's look at the source code. You have interfaces, you have classes, and then you have lambdas, both static and non-static. On each iteration, the methods look the same. If def is 0, you return a static object. Otherwise, you do a recursive call and you call the same method. Let's look at the results. Right, so for lambda and static and non-static, all three JVMs are pretty much the same. For interface and static, non-static, and classes, the trends are similar. So I'm just going to explain one of them. So what happens is that C2 will always do a virtual call for each iteration, and basically it doesn't inline, so it does the virtual call and then decrements that number by 1. Then GraalVM, EE, and C are able to inline, but up to different depths. GraalVM C is able to inline up to a depth of 6, and then GraalVM EE is able to inline up to a depth of 8, and this can be seen in the assembly code. So I'm not trying to bore you too much here. This is a subtract by 6. This is CE, which inlines up to a depth of 6, and then I'm going to call this 6 layers deep, right? Do you have enough time for the last one, or do you want to?
I think, yeah, we can end up here.
Yeah, okay.
No, I think this is...
yeah, it's okay, yeah. This was another one, but you can read the article if you're interested into it. We are kind of running out of time now, so Ionuț will going to continue and present you the conclusions. Yeah,
we have a lot of such. It's very difficult to cluster what's more important. But what happens, what's next now, just a few slides, and I promise it's a bit easier. And we don't have any instruction code in this section anymore. The question which arises is, okay, you presented us some benchmarks, but yeah, some of them are good in favor of one compiler, some of them are good in favor of the other. So no compiler is perfect, that's the thing. We try to use a way to measure a final result. And for that one, we use this geometric mean. And we also found a paper how to do that, and this is the formula for this geometric mean. Basically, this x1, x2 until xn, it's each score that we got for the benchmark. So this x1, xn are all of our benchmark scores, and we use this formula to basically try to a bit understand what is the overall idea. And this is for x86 64. And Graal EJIT was a bit, is better basically overall, but be very careful. This is just about numbers. Take this with very much precaution, because basically if you add like 20 C2 benchmarks, which basically says, okay, C2 is basically better. So take this with very much precautions. We just did it because we wanted to assess the overall score. And that's why we created this normalized geometric mean with the formula that I showed you. But yes, don't trust us too much in this regard. But still, it's something nice, right, to have something tangible at the end. So in this case, for x86, E was good. C2 was somewhere in the middle, and anyway, we saw it also in the benchmarks. C has its very limited set of optimizations, less intrinsic, so it's under C2. On ARM64, it was more or less the same. So again, here, EJIT scored better. We didn't, so all the benchmarks that we showed, they were for x86, but we did more similar things for ARM64, and here as well. Basically, E was faster. Okay, these are some application developer guidelines, right? Because this is probably something that you should take away. This is something a bit more realistic. And we try to come up with some sort of criterias which type of problems better fits one compiler versus the other. Of course, we excluded the C because it said it's suboptimal. Doesn't make sense. Of course, in general, don't take it It's a lot of political stuff. But in essence, I think EE compiler itself, the Graal EE behaves better when deals better with a lot of allocations, deals better with when you have a lot of implementations for the same interface. It's able to further devirtualize. And it has better inlining heuristics, as we also saw in our benchmarks. It behaves for these nested or recursive calls. In general, it does a better job. Of course, there are also some class, let's say, of categories of problems where, for example, C2, we found it very nice for throwing exceptions. So don't be afraid to throw null pointer exception if you use C2 and if you don't use the stack traces. So this is optimized. Also, C2 has an extended intrinsic set, right? So this is much better. And this is the last one. It's overall, because C2, it's a native compiler. Graal, it's Java, it's written entirely in Java. And of course, it needs to be compiled during the runtime and allocated in heap, of course. This is one point. So it adds a bit of heap overhead besides your application allocations. And the second point is, if you do some sort of measurements, be careful, because Graal in general needs more time, more warm-up time than C2 to reach, for example, the peak performance. That's why, for example, C2 does it a bit faster. Graal needs way more iterations because it's written in Java. It needs to be compiled and so on and so forth. Challenges. Of course, we had a lot of challenges. The most important takeaways for me and Florin are written in here. If you do macro benchmarking and if you don't understand what happens throughout the micro benchmark, because it's not implicitly about numbers, right? Micro benchmarking is not about numbers. It's just to understand and be able to explain those numbers. Of course, this is the first indicator, but it's good to understand what happens under the hood. Second one is, you might think, yeah, all of these are micro benchmarks, but how does this help in my real application? That's a valid question. In general, micro benchmarking is not a good predictor of what would happen on production. But then this is my opinion at least, it tells you a lot of things. It tells you some strengths or some weaknesses that you can potentially prevent in some sort of cases. So even if it is not a good predictor, and also all of these micro benchmarks have ideal profilers, so it's not a polluted profiler at all, it is very clean code. It tells you key points from each of these categories. And one more thing, we also notice differences between architecture. So basically, if you say this is good on x86, it might differ on the other architecture, for example, ARM64. So this is not the same, because of course the instruction set is different. So these are not comparable sometimes. Just to reveal a bit, we also try to do this for garbage collectors, because this was mainly focused on compilers. The problem is it was misleading, and we drop everything regarding to garbage collectors. So doing micro benchmarking for garbage collectors is not very handy. That's why we stopped and throw everything away, and we focused mainly on the JIT versus on JIT from C2 and Graal. Future work, yes, it is something what we aim to do. Basically, we aim to finalize our JDK 11. We walk backwards from 17 to 11. The thing is, we ran all the benchmark for 11, but we didn't interpret anything. So I think a summary would be nice. And of course, we will be looking to get the 21, the next LTS. So as you can see, we are mainly focused on LTS releases, which, yeah, I think it's good enough. And of course, in parallel, Florin and I will be looking to extend the benchmark suite. And this is also a request to you. If you like what we did and if you are interested in, feel free to contribute, because actually everything is public. So we have the repo here. Everything is written here. All the benchmarks, all of our setup, everything is here. And that's basically it. We would also like to thank you to all of our reviewers, all of the list of reviewers, and it's mainly written in the article. So yeah, because without reviewers, it's even more difficult. And that's it. Thank you so much. I hope it was interesting. Everything is public. I also make these slides available, so if you have any ideas, if you have any questions, we are here and happy to answer. Yeah, thanks so much.